Well, good evening and welcome to the Marjorie Lynn Banks Lecture Series, Making Conservation Personal. I'm Chris Holan and I'm our Chief Conservation Officer, and I just really do want to extend a welcome to you here tonight, and particularly to our Scouts. We're very honored to have the Boy Scouts with us tonight, so thank you. Throughout this series, we have been very privileged to bring to Baltimore individuals who have devoted themselves to creating positive change in the world, whether they're addressing climate change and resiliency, like Dr. Ali, whether they're improving ocean and human health, or they're building much-needed diversity in the conservation space. We believe their stories can offer insights and inspire us to make this blue planet a better place for all of us. So the Aquarium has had the pleasure of hosting these Marjorie Lynn Banks Lecture Series now for more than 15 years. And this is thanks to the generosity of the Bank family. And as many of you know, Marjorie was a photojournalist, she was an environmentalist, a diver, and an explorer. And when she passed away in 1994, her family endowed these lecture series in her honor. And it has been deeply gratifying for the Aquarium to play a part in sharing Marjorie's love of the ocean and her sense of adventure with the community. So we really do appreciate the Bank family for allowing us to do this. In addition to recognizing the Bank family, we do want, for making tonight's event possible, I'd also like to acknowledge the entire Aquarium family of members and donors, because we really, without you, it would not be possible for us to connect people with the aquatic world through our exhibits, our education programs, which many of you have participated in, our conservation initiatives, which are growing each day, and more. And so I would just say this, what I'm going to say, is if you are not yet a member or a donor, we encourage you to become one. We think the value is good, and we think that it's particularly important in this day and age. We are a nonprofit, and it's a time period where any type of donation, should you choose, we would be honored to have you join our family. But we do appreciate every donation and gift. And we also appreciate our staff members. We have staff here tonight who can answer any questions, and I'd really like to acknowledge those staff, because our staff and our volunteers are what really make this place possible. It takes a tremendous amount of work, and we really do need all of our staff and volunteers. So I would say this, that I've been fortunate to be with the Aquarium almost 2 years now, and it is really, I would say, it's inspiring to work with people who are so passionate about the mission. I mean, everybody here really cares deeply, and they really want to inspire conservation of our world's aquatic treasures. So, thank you to our staff and volunteers, particularly our volunteers. At the Aquarium, we have 3 overarching conservation themes and guiding our work, and one of them is climate change and resiliency. We are an urban aquarium, and we are also a coastal aquarium. And as a result, we think it is our responsibility to stay focused on the topic of climate change, educating our guests, and conducting resiliency projects. We care deeply for our surrounding human community. We know that a lot of, particularly in urban areas, a lot of the vulnerable populations are being, overly burdened with the impacts of climate change. We also care about our ecological diversity, and as well as our ocean's health. So we are definitely committed in staying the course on the climate change and resiliency theme. And that is why we are so honored tonight to have Dr. Richard Ali as our guest. He is the Evan Paugh University Professor of Geosciences at the Pennsylvania State University, where he has worked since 1988. His research interests focus on glaciology, sea level change, and abrupt climate change. He is widely credited with showing that the Earth has experienced abrupt climate change in the past, and likely will again, based on his studies of ice cores from Greenland and West Antarctica. And we all have been seeing, obviously, more and more severe weather events. But even more exciting than all of the work that he's been doing and predicting is that Dr. Ali participated in the UN Intergovernmental Panel on Climate Change and was co-recipient of the 2007 Nobel Peace Prize with former Vice President Al Gore. Dr. Alley doesn't always necessarily want us to mention that, but I think it's pretty impressive to be with a Nobel Peace Prize winner, so I'm mentioning it. He was also elected to the National Academy of Sciences in 2008. No small feat to do that, so as you can tell, we're excited. Additionally, he hosted the PBS miniseries Earth, The Operator's Manual, and authored a book by the same name. His popular account of climate change and ice cores, The 2-Mile Time Machine, was a Phi Beta Kappa Science Book of the Year. I mean, Dr. Alley, his true gift is he makes science accessible, and that's what you're going to hear tonight. He has been compared to a cross between Woody Allen and Carl Sagan for his enthusiasm, which, you know, that's an interesting comparison, really. So we shall see. And for his enthusiastic efforts to communicate the excitement and really the importance of science. And tonight, we're going to get to learn what makes him tick, what keeps him going, and what inspires him. So with that, let me bring up Dr. Alley. Thank you.
Well, I don't know what I do after that, but at any rate, thank you. It is an honor and a privilege to be with you here tonight. And thanks to a few, the Family Emerging Bank for supporting this. This is a great lecture series in a great place. And the National Aquarium this is a treasure, and it's wonderful to have it here. My friend Ryan Walker here helped get me down. Maggie has sort of put everything together. I'll show you a picture of Christopher Schumann later. He's in the back there. So I'm going to use a bunch of penguin pictures that have virtually nothing to do with what I'm talking about, but penguins are cool. So at any rate, I'm going to show you some penguin pictures. We'll walk through a few things, and then we'll see where we can go with it. So like I say, I'm going to do penguins. I'm going to do a little background, and then we'll get to climate change, sea level rise, and then I'll finish with what I hope is something a little bit uplifting. I hope I scare you a little bit on the way, and then we get to good things at the end. So with that, probably no one in this room needs to be told this, but some of your neighbors probably do. That science really does work. And that we're here because at some point our parents or our grandparents or we were cured of some disease by scientific medicine. And that they take a computer model and they design a new airplane and it flies the first time you take it out of the hangar. And I spend a lot of time now waving this around. This is my cell phone. And there's a nice lady in here who tells me where to go, and I go there. But the nice lady is canoodling with Albert Einstein because there's a GPS in here, and that GPS actually uses special and general relativity to figure where you are. And if it didn't have relativity, it would drop you in the bay out here in a day or so. It actually does. Relativity is functioning in your pocket. And quantum mechanics is functioning in your pocket. And you think about it a minute. What is a cell phone? It's a little bit of sand, it's a little bit of oil, and it's the right rocks, and science and engineering, and a little marketing and design, but that's all it is. It's sand, oil, and the right rocks. And science turned it into this thing that has such fantastic abilities. But we have fellow citizens who will take this and send me a note that says, you scientists don't know what you're talking about. So it's worth remembering that science really, really, really does work, okay? And science advances. Newton learned an amazing amount. There were things Newton missed. And so we did need Einstein and Bohr so that we can have the lady tell me where to go. But we didn't throw away Newton. When they designed this building, they did not write a quantum wave function for it. This was designed with Newtonian physics. And when I model flow of glaciers, I use Newtonian physics. And basically, we have never thrown away the useful parts of a big piece of science. We really do get better and better at doing things that help people. Okay, now, I'm going to in particular come back to energy. So if you got the pretzels out there, you're pushing your 2,000 calories per day, okay? So you know, a human diet is 2,000 calories per person per day. That's equivalent of 100 watts averaged over the day. So all the brilliance that you do uses the same energy as that light bulb. Right? You do way better than the light bulb. But in point of fact, if we had to run the light bulb by riding a bicycle to make the electricity, I'd be out of breath, okay? But I don't. And Cindy and I drove down here this morning, and you know, we didn't have to spend the summer hoeing corn so we don't starve to death this winter. The energy that takes care of us is more than 200,000 calories per person per day, 10,000 watts. Right? And we love this. And right now, it's about 83% fossil fuel. Okay? So that's a big deal. And that is going to be a bigger deal. Right? So I'm a climate scientist now. I started as a geologist. I'm a climate scientist. The cell phone can pull the signal out of the noise of the sun and the microwave ovens and so on with filters that were designed by Fourier. 1829, Fourier says the surface of the Earth is a little warmer than it should be. The atmosphere must be doing something like a greenhouse. Greenhouse effect, 1829. Tyndall in 1859 says, CO2 is doing it. By 1896, Arrhenius says, hey, we burn fossil fuels, we're raising CO2, this is how much we're going to warm the Earth. He was pretty close. Okay? Putting it into a modern quantum mechanical version was done by the Air Force right after World War II. The Air Force was not doing global warming at that time. They were doing sensors on heat-seeking missiles. And the CO2 absorbs infrared, whether it's coming from the hot exhaust of an enemy bomber or whether it's coming from the sun-warmed Earth. The idea that somehow we don't know what we're talking about on this is completely absurd. This is old science, and it is very, very well-established science. We burn fossil fuels, we raise CO2, that changes the climate, okay? How much? Arrhenius told us how much it would warm. What he didn't know is how good fossil fuel companies would be at giving us what we wanted. And the numbers, right, so you know we can't see the CO2, but it's real. The numbers, you know what trash looks like. There's a lot of good recycling going on out here, but there's a lot of things in the US that are not yet recycled. In the United States, per person per year, we put out at the curb for the trash collector a half a ton of trash. Each of us, on average, is responsible for a half a ton of trash. And our share of the CO2 produced by the fossil fuels from all those coal mines and all those oil wells is 19 tons. Half a ton of trash, 19 tons of CO2. And this has to change the climate because it's physics. And we know it's happening from the physics. The models confirm this. The data show it. The history shows this has happened in the past. Okay? And if we don't change, the impacts are going to get bigger and they're going to get worse. And we know this with really high confidence. And we also know, and this is the thing that's so wonderful, there's very strong scholarship that if we take our knowledge and we take you Boy Scouts and you commit to building a better world using our knowledge, we get not only a cleaner environment that's more ethical, but we get a stronger economy with more jobs and greater national security. Right now, if you want to help the economy, it's the same direction as helping the environment. And we know this with very high confidence, okay? We are very close to building an energy system that will power everybody on the planet essentially yet forever and get to everybody the good that we enjoy right now from the fossil fuels. We can do this. We can build something that would make us energy rich for the first time in history, farming energy the way we learned to farm food. And this is a wonderful vision. And I've had the opportunity to play a very small role in learning just how good things could be if we use our knowledge, and just how bad things could be if we don't. And we're on the cusp of one of these now. We use the knowledge, and we can build something fantastic. Deny the knowledge, and we can build very bad things. And so I'm going to walk you through a little bit of the bad things and then close with a little of the good. But so I'm a professor, and I enjoy being a professor. And my job description, right? This is my job description. I get up in the morning and say, what's your job description? It's go to gloriously beautiful places with some of the world's best people. Learn what nobody knows. We call that research. Share it with others. We call that teaching. And help them do good things with it. We call that service. Right? Great places, great people, learn what nobody knows, share it, help people with it. That's my job description. Right? This is so cool. I have been doing this for a long time, so I started out small a long time ago. So there's a penguin. It turns out I went to Ohio State. They were moving an office at Ohio State a couple of years ago, and they dug this up and they sent it to me. Right? The summer of 1977, I started working on ice. So I've been working on ice for 40 years, and that thing there is me. Okay. And so what I grew up in suburban Columbus, just north of the city, sort of hanging on the bottom of the middle class by our fingernails. And I desperately loved the outdoors. I loved hiking. I loved caving. I was a hobbyist. I'd cut and polish rocks. And so I went to geology at Ohio State. And then the best thing is I met my dear wife, Cindy, who's right down there. And we got married, and we worked for an oil company. I still trade Christmas cards with the supervisor. We went to Wisconsin for a PhD, great place. And I was working there. I have some engineering. I took the course on things that break, I'll come back to broken things. But I actually got into Greenland and Antarctica looking at how snow turns to ice without melting as an analog for the kinds of industrial processes they use to make useful things. And we were learning more about the physics by watching how the ice sheet did it. And it was fun, right? So sophomore year, I went to Antarctica. This is posed, drying the socks is not. Okay. So we got to go to Antarctica my sophomore year. I spent a lot of time going to Greenland, so we'd go get on these big ski-equipped Hercules airplanes and fly up to the top of Greenland. I was in the field for our first wedding anniversary. I was in the field for number 5, for number 9, for number 10, for number 12, and she still put up with it. So right? So I used to go to the field. This is midnight on the 4th of July in central Greenland. We're 2 miles up on ice and 200 miles from the nearest rock. And here's Wanda Kapsner, who did a thesis with us studying ice. And here's Kurt Cuffey studying ice. I'll come back to Kurt later. And Sridhar is a very close colleague of mine studying ice. And this is, if you've been there a month, even if it's freeze-dried laundry, it gets the socks clean. There's a theme here, Right? Okay. So at the time I took this picture, Chris remembers this one, right? At the time I took this picture, we had been there a month. And the newspaper was a month old because we had not been resupplied for a month. So that really is a month-old newspaper. But you know something? It doesn't matter. Okay, now I have this labeled a good day in Greenland because you know what a not so good day in Greenland looks like. Okay, so and we started watching snow turn to ice, and we came into making histories of Earth's climate. And this is what was so fantastic. So here, we're digging a hole in the snow. This is Joan Fitzpatrick at the U.S. Geological Survey. The guy without the shirt there is me. And we're digging 2 holes. We're going to put a board over this one. The sun will shine in that one. We're going to climb down there. And what do we see is something like this. And so this is a picture of Christopher, who's there behind you looking at layers. This one's actually in Antarctica, but here's the one we were doing in Greenland. And this is winter snow, and that's summer, and that's winter, and that's summer, and that's winter, and that's summer. And we can do years. And if we can do years, we can do snowfall. And we can do snowfall, we can learn how much dirt was in the air that's diluted by the snow, and we can do the ice flow, and we can do temperatures. We can do an amazing number of things. So we got into drilling ice cores with these big drills. We had T-shirts that said, "Big boots, big science," right? And here's an ice core. This one is from almost a mile down. This one's 8,000 years old, and that's a winter, and that's a summer, and that's a winter, and that's a summer, and that's a winter. And we counted these things, and we made climate histories. And then we went out to this big freezer in Denver, and we did some more of that. And I teach the class, I wrote some of the papers, I wrote the book, you know, and this is this vast, huge field. There are so many good scientists all around the world, here in the US, here in the East, who are doing the history of climate. And what we eventually learn, the biggest picture, right? Climate has always changed. That means climate is changeable, right? There have always been fires in California, which means it was possible for a bad person to set a fire. And you worry about arson in a place that there's always been fires. You worry about us changing climate in a place that climate has always changed. Climate has always changed. We often learn about the climate changes, not just from our ice cores, but from what it did to living things. And it made them migrate, or it killed them. And so climate changes have always affected living things, so climate change is important. And then the third one is that many, many things change climate. But over the history of the Earth, CO2 has been the single biggest one. And we could make changes as big as the biggest things that nature has ever done, and we could do it faster. And so the vast story of drilling ice cores and looking at sediments all over the world comes down to confirm what the physics told us. We're gaining from the use of fossil fuels, but we risk really big things. Okay? So I'm still just a small player in this, but it's opened some fascinating doors for me and some personal experiences that have just been amazing. There are senators in that helicopter. I got to go to Greenland with 10% of the Senate, which was really cool. I've testified to the House, I testified to the Senate, I helped the Nobel Peace Prize winning UN IPCC. We're meeting in Paris there. I got to go bungee jumping. Oh, this was so cool. You know, we're filming their TV shows, and you toddle up to the edge, and you deliver the lines, and then you jump off. So, anyway, and then I like to brag. I shouldn't brag, I'm sorry. But something really important is I am I'm a friend of Phil. Right, science is a great gig. Science is a great gig. So now what I'm going to do is I'm going to jump into one issue that, if we don't change our ways with the warming, is a big deal to you here in Baltimore. And this is just one issue of many, but I want to walk you through this because it's a fascinating one. So we know in the past that nature raised CO2 and it got hot. And when it got hot, we know that ice melted. So on here, over here is not much CO2, and over here is a lot of CO2. And this is sea level. We're there, and in the past it's been lower and it's been higher. And if I do the simplest thing, and I connect the dots, I take where we are now in CO2, I run it down to the line, and I run it over, and sea level there is, 50 feet higher than it is now. And 10% of humanity is underwater. And I'm not telling you that will happen. I'm telling you this is a really good reason that we should understand what's going on. Because us raising temperature could be a big deal, especially given that we could put CO2 over here if we don't change our ways. And that's 200 feet of sea level. Okay? And remember, even sometimes a little bit of sea level rise matters a lot. So this happened to be Hurricane Gustav in New Orleans, and it did not get over the levee into the city. Right? But sometimes they do. So yeah. So sea level is rising. 1993 on your left, 2017 over here on your right. This is altimetry data, so this comes from NASA and NOAA. And yeah, sea level is rising, but so far it's pretty slow. A foot would take about 190 years for a foot. Right? If I take this and I squish it way down into that little tiny box, that's the previous plot, and I show you what happened before, that's because we started warming the world. And if I show you what's coming, those are our decisions. We could keep it below that, we could put it above that. But those are our decisions. We decide what happens in the future. And what I'm going to show you is that it might even be way above that. And that's important, okay? So, sea level rise, what controls it? All right, so glaciers are melting in the Alps, glaciers are melting in Alaska, glaciers are melting all around the world. That takes water off the top of the mountain and it puts it in the ocean. That raises sea level. But there's only about a foot of sea level in the world's mountains. And when the mountains run out of ice, you've only raised sea level about that much. The ocean is warming, and that takes up more space, but it takes sort of 1,000 years to warm by a degree or two, and that's only about that much. Greenland is 24 feet of sea level. You melt the ice off Greenland, sea level is 24 feet vertically. We're probably underwater in this room at that point. Antarctica is 186 more. We're underwater, don't kid anybody. Okay, and just as a scale, this is the height of the Lincoln Memorial to scale on this plot. So if so if we melt Greenland from the bottom of the steps, Abe has got water in his lap, and if we melt Antarctica, Abe's in trouble. Okay, so or you are. So 6 meters, 20 feet. This is less than Greenland. And you can come up here somewhere and ask what's underwater, and it's not very pretty. That's 6 meters. If you remember Superstorm Sandy just up the coast here, the highest surge from it was only 13 feet, 4 meters. These are numbers in feet, 5 feet, 5 feet, 6 feet, 3 feet, 8 feet there. That's all that Sandy was for a few hours. But that's what Sandy was. And West Antarctica or Greenland could be, by themselves, could be sandy for all the world's coasts essentially forever. Okay? There's New Orleans when Katrina got over the levees, right? And you can see the scientific literature now. We determine which cities go underwater. We could melt all the ice in the worst case. Okay. So the ice sheets this is sea level rise from Antarctica, this is sea level rise from Greenland. They are already contributing, they're already shrinking and melting as cold as they are, but they're not going very fast yet. Right, and I've got an analogy on here. That plot, this rate of shrinkage, it would take 100,000 years to get rid of the ice sheets. Right, now suppose that I had skipped the pretzels tonight. Suppose that I went on a diet and I was really good for the next year. And I lost weight at the same rate that the ice sheets are doing, 1 part in 100,000 per year. How much is that? It's 1/3 of one of those potato chips on me. Right? So right now, the ice sheets are losing weight at the rate of 1/3 of a potato chip per professor per year. And I could lose it a little faster and it would be good, but if the ice sheets lose it a little faster, that's really bad. And they could. And the thing is, they could go much faster. So what I'm going to do is I'm going to teach you, I told you Kurt Cuffey worked with us, he's now a professor at Berkeley. He wrote the book in our field, The Physics of Glaciers. I am going to teach you the physics of glaciers tonight. Okay, you're all going to go out of here as glaciologists. You're going to be masters of this problem, right? So here it is. This is my dear wife pouring a pancake. What happens if you make a pile of pancake batter? It spreads under its own weight. If I were to pour this water on the table, it would spread much more rapidly. But when you make a pile, it tends to spread under its own weight. If you hold it back, it doesn't spread as fast. If you make it stronger, it doesn't spread as fast. If you pour it on a bumpy, sticky bed, it doesn't spread as fast. Okay? This is the physics. It makes really cool patterns, too. You're going to see these again. But the physics is, if you make a pile, it tends to spread under its own weight, and it cares about how strong it is, how bumpy and sticky it is, and whether you're holding it back. Okay, so get that physics. Piles spread depending on how strong, how bumpy, and whether you're holding them back. Okay? So, get up in a satellite. Look down. If you've ever been to Alaska, that's the Juneau Airport. This is the ocean. The red is actually trees. This is one of those NASA false color images. And what is this? It's a pile of snow. And it snowed on top of the mountains, and the snow built up and built up and built up, and it spreads under its own weight just the same as that does. And if you've ever been to Juneau, you might have gone to the Mendenhall Glacier. What's the Mendenhall Glacier? There it is. It's a pile on top, spreading under its own weight, and it's going down the valleys of the waffle iron of Alaska. Now, what it looks like on top, here's Don Voigt and there's Kaya Riverman, Penn Staters teaching at the Juneau Icefields Project. So that's what it looks like on top. But it's a pile of snow spreading under its own weight. Here's another one just right along the coast there. If you've ever taken a cruise to the Hubbard Glacier, that could be the Hubbard. That could be the Malaspina. Okay. Cape Cod. There used to be a giant pile of snow up on Greenland, or up on Canada, and the ice came down like that. Just like that. Okay? Right? And so what are Greenland or what are Antarctica? They're just bigger piles of snow. The snow piles up, it squeezes to ice, more snow's on top, it spreads under its own weight down to the coast where it breaks off or melts. It tends towards balance, piling, spreading, melting, and breaking. If we make it warmer, it shrinks and the ocean grows. Right? So, let me show you a couple things that are really cool. Right? So if you were to take this and spray Pam on it, something that would make it more slippery, it will spread faster. This is true of ice sheets too. So here, the edge of Greenland, in places, the ice sort of flows over the waffle iron, and it gets little low spots, and then when it melts, the low spots fill with water. And this particular one is about 2 miles across, and it's about 30 feet deep in the middle. And you can see some others out there. But there's cracks underneath, and the water can wedge open the cracks. So a former student of ours, Sarah Das, is standing in one of these lakes. I forget which one she's standing in, but she's standing in it right there. Except the lake went to the bottom of Greenland, and then it went out the front, and it lubricated the waffle iron to let it go a little faster. And thank goodness Sarah was not in her boat on the lake when it drained. It flowed into the crack at twice the rate of Niagara Falls for an hour. Whoomp! And oh man, and these blocks were bouncing out of the holes and flying around. It was just truly dramatic. Big earthquakes and all kinds of excitement. And so this is a very interesting thing. But fortunately, even if you spray Pam on that waffle iron, it's still bumpy. And even if you break through and make this really slippery, it's still bumpy. And so the ice sheet didn't fall in the ocean. Okay. But remember what it did when it broke through, because we're going to see this again. Okay? So if you hold it back with your spatula, it doesn't spread as fast. Right? Another analogy. Right? This building tends to spread, but it's like the cooked pancake. The building is strong enough that it isn't bulging much at the walls. The builders of Gothic cathedrals pushed the limit. And they started having the roofs sag in and the walls bulge out. The spreading tendency was beating them. And so they had to come up with the flying buttress to push back again. You know, and all flying buttress is sort of this, right? Push back against the wall so it doesn't cave in. If you're in a hurricane and the house walls are breaking, you wedge them, right? So that's what a flying buttress is. And ice sheets have flying buttresses too. So here's the diagram of your Gothic cathedral. Here's one that Cindy made for me of the ice sheet. The ice spreads under its own weight. It comes down to the coast. If it's cold, it flows over the ocean without breaking off. And then it'll run aground on a little high spot in the bed, or it'll be in a bay and it'll scrape past the sides of the bay. And this friction holds the pile back the way this friction holds the pile back. If you were a bad person and you wanted to hurt a Gothic cathedral, you could break the flying buttress. What happens if we warm the world and break the flying buttresses of the ice sheet? Right? And I'm going to show it to you. This is some work that Christopher did. We are down here on the Antarctic Peninsula. That's that finger that sticks up towards South America. Black is ocean. The mountain range is over there. This is the flying buttress, 12 miles, right? So these little icebergs are bigger than aircraft carriers. This thing formed 10,000 years ago as the ice was shrinking back from the Ice Age. And it sat there for 10,000 years as of January 31st, 2002. And you remember the lakes. See those? Those are lakes formed by warming around the ice shelf. And what happened to Sarah's lake? It broke through. What happened to these lakes? They broke through. This is 5 weeks, okay? Now this blue slushy, you could probably kayak through that. It's just broken up stuff, but all these things just sort of fell over. The thing fell apart. Now that did not raise sea level directly. It was already floating. But you lost the friction on the sides the way you would lose the friction of holding up the wall from your flying buttress. And so what happened after that is this one's going 8 times faster. You lose that friction, the pile spreads faster, and that takes ice that was not floating, puts it in the ocean, and that raises sea level. Now, fortunately, there wasn't much ice behind that, just a little bit. So you can't raise sea level a lot with that one. What we're worried about is this one and this one and this one and a whole bunch of others with a lot of ice behind them. And it hasn't gotten there yet, but if we make it too warm, it might. Okay? Now let me tell you exactly the same story from the other end. So this is Greenland. We're going to go in along this yellow arrow towards Jakobshavn. Okay? Jakobshavn is just a fast-moving piece of this big ice sheet that we gave a name. Jakobshavn had a flying buttress. The water warmed, about 1 degree Celsius. The ice shelf broke off and left a cliff. This was probably the fastest glacier on Earth, and then it tripled. Probably the fastest glacier on Earth tripled. Okay? So here we go. That's the yellow arrow there. And the blue arrow there is up there. This is tundra. This is tundra. This is a very deep fjord full of ocean water with broken up ice on top. And I'm going to show you 2 pictures. First, I'll show you that this is water under the broken up ice. There's a seal. We're in the helicopter with the senators, and they actually do oceanography with these seals. You put instruments on them, they swim around under the ice, they come back, and they tell you what was down there. And then the seal was down here, and here comes the ice, and there's the cliff that was left when the flying buttress broke. That's the wall of the cathedral. And it's 330 feet, sort of, and 9 times that below the water. Right? This is 2/3 of a mile high. Just for reference, I went on the Wikipedia and I pulled this out. I'm not endorsing any particular building, but this is just a shade taller than that cliff. So to scale, there's the Lincoln Memorial, there's your building, that's the cliff, 9 times more below, right? Stack 9 more of these on top of each other. The next photo, I'm in the helicopter with the senators and we fly by there. Okay, I put this over here, I sort of scrunched it, but that's the right height, right? And right, I'll get it out of the way now, but the pilot says, how close do you want to get? And I was not this eloquent, but I basically said, look, if you saw this building with a crack in it that went down to there, how close would you get? Right? I mean, come on. So I'll show you what happens, right? So here we go. There's the building, there's the Lincoln Memorial, there's the cliff, and it is breaking. These pictures start while it was breaking. This is 50 stories high. You're going to see a 50-story high splash, right? I mean, just watch this thing. It is just unbelievable. It's a 50-story high splash. I'm running it backwards now. I could just stand here all day and run this thing, right? This is just unbelievable what these things do. They make earthquakes that you can hear here with a good instrument, right? But what it does now is it breaks, and then it waits a while, and then it breaks, and then it waits a while. If it were higher, it would break faster because the stresses would be bigger. And what we're worried about is one that's going to be higher. Back to Antarctica, the flying buttresses are in this funky cream color. The gray is places that have rock above sea level. But everything else could raise sea level and can make icebergs. And this piece, if it retreats out to here, will have a cliff that is fantastically higher than that one at Jakobshavn. And it would break faster. And when we take the physics of that and we put it in a model and we say, let's make it hot and see what happens, what does it do? It raises sea level about 15 feet, sort of as fast as we let it. In the lifetime of you Boy Scouts, we could flood everything out here. Right? That's possible. And so I'm going to show you something. And then I'm going to review and we'll quit. But I commute on this bicycle. I do not have to drive around 695. I am deeply grateful for that. Okay? But I want you to think about these poor schmoes out on 95 or 695 and ask, what does a commuter face? Right? And what I'm going to show is how likely is it against how big the problem is. Right? So what does a typical commuter do? You get out there on the interstate and you get stuck in traffic. Right? You turn on the radio and it's boring. Okay? That's the most likely thing. What's the best thing that can happen? It's really unlikely that there's no traffic and they're doing the Beach Boys Festival, you know? But that's not what happens to you. You get stuck for an hour and they're testing the emergency broadcast system, right? But why do you get stuck for an hour? Sometimes it's because a drunk driver ran over somebody and they're dead. And we know this, that there is some chance of really bad things, which is not balanced by a similar chance of really good things. And what do we do about that? Our car has airbags, it has crumple zones. When we had the kids, we put them in kids' seats, we put on our seat belts, we have insurance, we have traffic engineers, now we have cars that are self-braking to keep us from running over things. We put a lot of money into something we don't expect to happen because if it does, it's so bad. Now, when we talk about climate change, if we use our knowledge wisely and what we expect to happen happens, using that knowledge makes us better off. And then somebody will say, well, couldn't it be better than that? And you say, yeah, it could. But it could be a little better, or it could be a little worse, or we could collapse the West Antarctic ice sheet, or kill off the Brazilian rainforest, or the coral reefs, or collapse civilizations. There's all kinds of bad things we could do. And there isn't really a good just from changing climate to offset the bad. You can't turn the world into the Garden of Eden, but you can break things you care deeply about. And so this is what happens if we ignore our knowledge. It's bad. It could be a little better, a little worse. It could be a lot worse. We could really flood everything here. Right? Now, I'm not going to go political, but I have been in this congressional hearing. I sat there and did this. And I say, this is what we know, and someone says, couldn't it be better? And this is what we know, and someone says, couldn't it be better? And then they say, look, we've heard both sides of the argument. No. Okay, no. Yeah, okay. Now, I'm going to do just a little bit of review here, and then I'm going to close it. But it probably is obvious that I am a professor. The kids used to say I had a professor button. You know, they say, oh no, you pushed his professor button, he's about to profess. So, okay, so what I'm going to do for you is I'm going to try to review Kurt Cuffey's Physics of Glaciers, what we just did. I'm going to do about a 3-minute review. I'll spend a minute closing, and then we'll go to questions, okay? And I will close with a discussion question, but we're going to do this in G major. So what I'm going to do is give my dear life the clicker, and we will see if I'm even vaguely close to being in tune, and then we'll see what we can do for you. So I snuck a guitar back here, okay? So we're going to see what we can do. This is the review of the Physics of Glaciers in G major. So my dear, right? Oh, a snowflake out on a chilly night, or the ocean blue and white. Southern Cross is a guiding light and headed for South Polo. Polo, Polo, Southern Cross is a guiding light, headed for South Polo. 1 flake's a miracle, 2 a display, 3 you might wreck your car today, but make a 2-mile pile. They're on their way, flowing from South Polo. Polo, Polo, 2-mile pile, and they're on their way, flowing from South Polo. Are we lost, Cindy? Whoop, okay. Hang on here. Okay. We will figure out where we are in a minute. Okay. I'm sorry. Oh, I skipped a verse. Okay, I'm sorry. Okay. Over the albatross soaring through, the penguins fly in the krill-flecked blue. Got seals and skuas and great whales too, all playing round South Polo. Polo, Polo. Seals and skuas and great whales too, playing round South Polo. Now just a little repetition. 1 flake's a miracle, 2 a display, 3 and you might wreck your car today, but make a 2-mile pile, and they're on their way, flowing from South Polo. Polo, Polo, a 2-mile pile, and they're on their way, flowing from South Polo. Now physics. The physics is simple, all piles spread. Water batter, or cats on a bed, or a continent-wide 2-mile pile snow-fed, spreading from South Polo. Polo, Polo, you got a continent-wide 2-mile pile snow-fed, spreading from South Polo. Slow in the middle, thick and cold, down through the mountains, carved in old, picking up speed in the ice streams bold. Don't fall in a crevasso, 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 picking up speed in the ice streams bold. Don't fall in a crevasso. Ice streams at the sea don't make bergs right away. No, they flow across the ocean for many a day. There's a great ice shelf in a rock-bound bay with friction from the side. So side, so you got a great ice shelf in a rock-bound bay. Friction from the side, so if we raise CO2, warm the air and sea, and melt the shelves away and let the pile spread free, it'll raise the ocean towards you and me and shrink that 2-mile pile-o, pile-o, pile-o. Raise the ocean towards you and me, shrink that 2-mile pile-o. Oh, an Arctic fox on a chilly night at the edge of another ocean, blue and white. If we melt their ice, would that be right? Both poles are on the same trail-o, trail-o, trail-o. If we melt their ice, would that be right? Both poles are on the same trail-o. Oh, a snowflake out on a chilly night. So you are all glaciologists now. I will show 2 more slides, and then so you're all glaciologists now. Summarize, science is a fantastic career. I am so blessed to have done this. I'm so happy that you came out to share it with me. Science is a fantastic career. And if we use our knowledge with commitment to where we want to go and with respect for where we came from, we help the economy and employment and the environment and ethics and national security. This knowledge is useful. We can use it. We can help all of these things. We can help penguins, and we can help people. And we have 2 daughters there. One of them now is teaching geology at College of Worcester. One of them teaches middle school science outside of Seattle. We can help them. We can help future generations. So let me quit with this. We really can have a world with icebergs and rainbows if we use our knowledge with respect and commitment to help people. Thank you.
Thank you. I don't think we have had such a passionate, knowledgeable, and talented guest before. So thank you so much. And we are going to move into being able to ask some questions of Dr. Alley. So you are all given cards. If you have questions, Maggie and others will be picking them up, and we can ask them for you. And while we're doing that, we'll just start with one that I'm sure you get asked this question quite a bit, is what is your favorite response when you meet people who don't believe the climate's changing, climate change deniers? What have you found to be the most effective response?
Yeah, it sort of depends on who they are and what they're worried about. And some places, I say it's not changed. Say, look, it is. And you actually do know this, and you see it, and so do your neighbors, and so do lots of neighbors. People get it. A lot of the sort of, I deny the climate is changing, is linked to, I'm worried about what the response will do to my job, to my town, and so often it requires going to the discussion of the solutions. And the fact that we actually do now know that dealing with this wisely will help the economy and will help jobs and will help national security as well as the environment. I think that is very underappreciated.
Mm-hmm, mm-hmm. Anytime, I think you're exactly right, you can make it personal and the basic needs of people, then people can see it. So that is a very good point. Another question we had was, so what were you like as a kid?
Oh, I was a complete nerd. Okay. I was probably, I really did. I got polished rocks and I got good grades, but I wasn't the most socially adept, I'm still not. But I thought, now you see me as this giant towering 5'7" person, but I was mostly the shortest kid in class for a long time. So.
While as a kid, what were you? When you were a child, did you envision this future? Did you envision yourself sitting, sitting right here at the National Aquarium. No, did you envision yourself doing all of the great work that you've done?
I was hoping maybe I could get outside and, whatever job I had, I could do some interesting things outside part of the time. And so you sort of want to get somewhere and maybe have a wonderful wife and some kids, and then be able to go out and do interesting things. And boy, have I been lucky on that.
That is great. That is great. And what would you say to, we have the Boy Scouts here, what would you say to youth that might want to pursue science, particularly today where science may not always be, being looked at as appreciatively as it has in times past?
Oh, you're so important. You're so important if you do this. It is the 15,000 years ago, we were still hunter-gatherers, and we were busily spreading around the world, causing mass extinction. We stomped into North America, our ancestors did, and it was just steaks on the hoof. It was mastodons and mammoths and all these wonderful, and we killed them. And then we learned to build and to grow and to farm and to learn and to teach. And there are 1,000 times more people on the world today than when we were overpopulated as hunter-gatherers. We became farmers, and there's, if we tried to go back, of the next 1,000 people you meet, maybe one survives. Our knowledge is why we're here. And contributing to that knowledge is as fine a thing as you can possibly do. We need engineers, we need marketers, we need designers, we need people who are committed to their job across the spectrum. But contributing to that basic knowledge is as wonderful a thing as you can do, because that is what we rely. Just to go back to, Einstein in my phone. Who would have possibly believed that relativity meant that I could drive down here and know where I was within, this phone can tell if I walk across the stage. And it has to have relativity and quantum mechanics to do that.
That's right. That's right. Well, when you were in the helicopter with the senators, what was their reaction to seeing those changes in person? Probably.
Yes. No, my impression, so I have had a small number of opportunities to talk to senators. Most of them get it, and they get it seriously. And they are more frustrated with what has happened in Washington recently than you are. But there's something that is bigger than any one of us. There's something that's bigger than the Senate. There's something that they are hoping that we will help them go back to doing what they were elected to do. That's my impression. That's an opinion. I couldn't prove it. But I was blown away with how smart, how dedicated, how funny, the joke-telling, the personability of the senators, and how much they actually know, and how much they are constrained by a system and primary elections and so on that they can't control.
That's actually comforting that they know more than we may think they do. So, and we'll take great reassurance in that. We have had someone ask us, what is the biggest reason the oceans are warming, and what can they do to help the climate? What would you say? Right. Somebody said, what can I do to help?
Right. So, biggest reason is CO2. That's very, very clear. Our fossil fuel burning is raising CO2. That's causing the warming. We got this. What you do is two things. One is the big picture. You vote, if you're old enough to do so. You talk to your neighbors. You engage with making the science useful. And I'm going to do something here, if I may. Cindy, would you click very quickly to forward? Right? Okay. This is a map of opinion in America. Blue is less than half believe this. Orange is more. Okay, so does America believe climate change is real? Most Americans do. Click the next one. Are we causing it? Most Americans do, but most of America doesn't, right? So there's more people live in Baltimore County than live in Wyoming, right? So this map is funny, but click the next one. Do we agree? Scientists agree hugely on this. Somebody paid money to confuse America about this, okay? Click the next one. Is it bad? Yeah, most people think it's bad. But now, this is what matters. Two slides that matter. First of all, lots of people say, I don't believe it's changing, I don't believe it's bad, but when you say, are there smart ways to fix it? They all agree that there are. They may not want to admit there's a problem, but when you get to solutions, they say, of course we can fix it, we can do this, but are they talking about it?
Yeah.
We have the solutions, we're not talking about them. So the big thing is to do the big thing. Talk to your neighbor, vote, and then the other one is you can't solve it all. But if you really are committed, pick something. And it might be recycling, and it might be bike paths, and it might be solar cells, and it might be something else. But if you're really committed, there are people here tonight who have picked something. Pick something and help on that. You can't solve it all, but because this ultimately helps us all, getting over the hump into where it really helps us, if everybody picks something, right? And there's a whole lot of you here have already picked one or two or three, and I know you're ahead of me on this, but nonetheless, do the big picture thing, talk to your neighbor, and then pick something.
That's great. That's great. Particularly the talking to your neighbor. Are you biking, commuting to work? I hear that you bike like 2,000 miles a year, which is rather remarkable. Is that due to picking something as well?
That is part of it. Yeah, we've been trying to get by on one car rather than two, and we've done this for a lot of years. So I ride my bicycle. You learn fascinating things about kitty litter is not packaged for bicycles.
There's your takeaway for tonight.
But you do learn, and there are things, and I go down to the township council, and I don't complain about kitty litter, but I do complain when they try to block the, so there are things you can do. Yeah.
Yes. Well, based on your research in the West Antarctica ice sheet, have you found that ice streams are increasing in speed and further lubricating and calving?
Yes.
Okay.
Yes, great question, and absolutely many of them have increased. Some of them have not. Some of the East Antarctic ones haven't, but the big ones that we're worried about, the ocean warmed, it thinned the ice shelves, they sped up, and they're raising sea level, and they could go more.
Okay. Well, can we, somebody else wants to know, we know that, that it's increasing, but can we halt the change? But, can we not only halt it, but can we reverse what we have already done? Is that possible?
Right. So halting it, we can roll it over, and it'll take a little while, but yes, we can do that. Reversing it, of course, eventually nature will do it. If we get it in check soon, nature will take care of most of it. If we wait longer, then, nature will take care of it, but rather than doing it in 50 years, it's going to be 50,000. And so the more we put up, the longer that tail is. And the tail starts getting really long.
Yeah. What, and kind of a follow-on from the same person, is how easy is it to get a job as a researcher? And I guess maybe even specifically, the type of job that you showed us where you get to go to beautiful places and, your job description. Right.
So it is not as easy as I wish it were. There are fields that I think are just begging, and I keep waving my phone around, right? The material scientists, the people inventing the next material, the people inventing the next solar cell, there's a huge need for folks in these areas. Environmental science, right now, there's good support in Europe. There isn't quite such a good support in the U.S., but there's a lot of people still teach, and our daughter, younger daughter and son-in-law are teaching at the College of Worcester. They will do research with undergrads there, and so they will be researchers, and they probably will get to the field at some point, and they will do it with their students. Excellent. And the truth is, there's a lot of really good people that are K through 12 teachers, and there are teacher in Antarctica programs. There are things that can be done.
Yeah. So keep the faith. You can absolutely make progress. We have another person that has said probably a very important question of, when are you releasing your album?
There actually are. So we have made some videos of these under PSU for Penn State University Rock Video. And my dear wife makes them. And so we have a big online class and we do the reviews to classic rock songs. And so we have, you probably know that there are volcanoes around the Pacific. And that's the Ring of Fire. And you certainly know that Johnny Cash went down in a ring of fire. And so we come out and we sing about subduction is a burning thing. So you can find these on YouTube.
Wow. I'm going to move right on.
It feeds a fiery ring. Yeah. Sorry.
So we might get an encore is what we're hearing if we're good. Switching gears again for a minute, we'll get back to the music, but you mentioned before that you did have a stint working at an oil company at one point. What role do oil companies play in finding solutions to climate change?
Yeah.
Kind of a different approach.
Right, so they have a big role. So we know, when Cindy and I both worked for Mobile Field Research in Dallas one summer, and they were very good scientists. And there actually now is very good evidence that the scientists working for the oil companies told the oil companies reality. Okay, they knew. And so part of the role might be, the paper was published this past summer showing what information went to the front office and what information went back to the public, and they don't exactly look identical, right? So there is a role to sort of embrace reality and move it forward. And this is not my area. I did not do that research, but you can find the paper. It's refereed scientific literature. The truth is that the skills that the oil companies have put together are fantastic, and they have ability. They could apply those to hot, dry rock geothermal. And in the short term, gas can be a bridge to the future. So it turns out that it is very hard to build a lot of renewable energy, wind and sun, if you have coal or nuclear on the grid. Because they built the coal plants and the nuclear plants so that they just have to put out power. And you can't turn them down for a couple hours in the morning when there isn't much demand for power. They're not built that way. And so apparently now there are times out in the Chicago area that the electric price goes negative. They have to pay people to take power because there's so much wind energy on the grid and they can't turn down the other things. And if they replace those with gas, then you can build as much renewables as you want. And gas serves to stabilize it until you get enough batteries on the grid to make it work. So there's a huge role here. They can really help us transition. They have the power, they have the knowledge, they have the ability. The business acumen is fantastic.
Okay. All right, we have a two-sided one. I'm an environmental educator who trains others.
Thank you.
Informal science education, absolutely, to incorporate climate science and solutions into existing educational programs. I use metaphors a lot. I love your pancake waffle iron metaphor. May I use it? And will you share your presentation? I have a feeling that could be one of our staff people's questions, actually.
Yes, you may use it. Yes, I will share. Great, thank you.
Yes, it is very effective. It is very effective. And another person was wondering about, the state of the world today, where the United States has withdrawn from the Paris Protocol. So, what are your thoughts? Yes.
Yeah. The future markets that we're not acting rapidly to seize. We're not only hurting the future in the environment, but we're hurting the future in the economy. We're hurting the future in national security. And so I think there are probably people out there who are cheering because we're ceding some things to them.
Right. And not sort of looking at the long-term picture.
Sure.
So, but kind of going the other way, looking at this more positively, what are you most proud of in your career?
Oh, boy. our kids and the students that I've worked with. We have, and across a range of people. So I've worked with some postdoctoral fellows, postdoctoral researchers. I've worked with a bunch of students at all sorts of levels. Two of my colleagues are in the back of the room there. And they came and they helped us at Penn State, and they've gone on to brilliant work elsewhere. And we have people scattered around the nation and other parts of the world who have worked with us, who are carrying on this work. It's just wonderful.
And is that, would be correct to assume that that's what gives you hope? Or what would you say? I mean, because it is tough times right now, what's sort of your hope spots that you're looking at?
Yeah, I mean, we can, the progress of knowledge and a progress of ability to do this has been so fantastic. In 2009, when I started writing a book that we turned into the PBS series, solar cells were still really not competitive for anything except my calculator. And now pretty much every electric utility in America is either trying to embrace solar or kill it or both. But the prices come down so fantastically, so fast, that we now know that we can build a renewable energy system.
That's right.
And we know that once we have our power, we can help other people get it, or they will get it first. I mean, you're not quite old enough, but
I might be.
there are a few people. There are a few people in the room who remember that to make a phone call, you had to go stand next to the wall, and you had to be attached to every other phone in America by a copper wire. And we had dug up big chunks of Utah and Arizona and New Mexico and Chile to get copper wire to connect every single home in America so you could stand next to the wall. Africa is never going to do that, right? And the question, should they connect coal plants with copper wires, or should they put solar on the roof and wind outside and just overcrop their fields and jump right over us?
Right. We're hoping for the leapfrog.
Yes.
Yes. Well, and, a particularly important question was that somebody sent in was, whose football team, Penn State or Ohio State?
We won. We won. Yes. Okay. So.
All right. Well, I think we could probably go on all night because this is just fascinating. And you are, whenever you talk to somebody who so clearly loves what they do, you find that you could sit here all night and listen. And that's, you are a phenomenal communicator. And really, besides all your research work, the fact that you are able to communicate this so clearly is really, that is exciting. And it's been a real treat for us to get to have this lecture with you. So thank you very much for coming. And we also are going to let you know before you leave that finishing out this series, we've been so honored with people like Dr. Ali, Dr. Sala talked to us about marine protected areas. We had 5 gyres last month talking to us about plastic pollution. Next month we have former Ambassador Jim Joseph, who was the former ambassador to South Africa, and he has really been a pioneer in the conservation and diversity space, in particular in ethics and conservation. So he will be here on December 13th. But it's been an amazing series because of people like you. So thank you so much.
Thank you.